Welcome back. Now let's see how we can use this cylindrical coordinate system to solve triple integrals. In this figure we have a solid domain E in R3. This solid domain is the C coordinates of this solid domain, the C values of this solid domain is bounded by two surfaces, u1 of x comma y and u2 of x comma y. Now let's say if you project this solid E onto the xy plane, then we have a domain D on the xy plane. So if you look from the top, then you will see this domain D on the xy plane. And here domain D is expressed in polar coordinates. Now if you want to evaluate, let's say we want to evaluate a triple integral of f of x comma y comma c dv over the solid domain E. This triple integral becomes another triple integral in cylindrical coordinate system. But now we want to express x in terms of r and theta, y in terms of r and theta, and c in terms of c. So now this integrand must be in terms of the cylindrical coordinates. So each x coordinate must be replaced with r cosine theta, and y should be replaced with r sine theta, and c coordinate stays as it is. But now this volume element dv becomes r dc dr d theta. This volume element dv becomes r dr dc dr d theta. Again, this volume element dv becomes r dc dr d theta. Now the inner integral corresponds to the c variable, and c values are bounded by two surfaces. Okay, and here we want to express those two surfaces in terms of the cylindrical coordinates. That is why I wrote u1 r comma theta and u2 r comma theta, and the middle integral corresponds to the r variable. Now this figure says your r goes from h1 theta to h2 theta. So in general these can be functions of theta. So lower limit is h1 of theta, upper limit is h2 of theta, and the angle, the last integral corresponds to the angle variable theta, and theta goes from alpha to beta. And this is the way we convert a triple integral in Cartesian coordinate into a triple integral in cylindrical coordinate system. Okay. Now I want to talk about this volume element dv. Dv, so this volume element dv has a shape like this. In cylindrical coordinate system, this volume element looks like this. And this distance is dr, this arc length is r d theta. So this one r d theta, this is dr, and this height is dc. Now this volume element dv becomes the volume of this small element, which is simply the height times the area. Now in chapter 12.3 we talk about the area in polar coordinate system. Area of this part is r dr d theta. Therefore the volume of this element becomes r dc dr d theta. Okay. Usually I prefer to do this order of integration. So this c variable can be expressed in terms of r and theta, and next what we do is we expressed r in terms of theta, and finally we have constant limits for theta. Okay. Let's consider this example. Let's say we want to evaluate triple integral of c squared x squared plus c squared y squared over a domain E, and here E is the cylindrical region determined by x squared plus y squared less than or equals to 1 and -1 less than or equals to c less than or equals to 1. Okay. First step is to draw this solid E. Let's do that. X squared plus y squared less than or equals to 1. This is a cylindrical region, and so basically you should have a cylinder with radius 1. Cylinder with radius 1. Let's draw the coordinate axis. X, Y, and Z. Okay, now the C values are bounded by two planes. Let's say this is the plane C equals to 1. This is the plane C equals to -1. Okay, and this cylinder is x squared plus y squared equals to 1. Okay, so my solid E, our domain E is this cylindrical portion that lies between the surfaces C equals 1 and C equals -1. Should be this part, this entire domain. So this is your E. Okay, let's convert this triple integral into a triple integral in cylindrical coordinate system. we have. Now we can factor out c squared from the integrand. V of the solid A. Okay, so if you convert an integral into an integral in the cylindrical coordinate system, you should have r, theta and c variables. Okay, so now we know that in cylindrical coordinate system, x squared plus y squared equals to r squared, and this volume element dv equals to r dc dr d theta. Okay, now let's figure out these 6 limits. The inner integral corresponds to the c variable, and c values goes from -1 to 1. C varies from -1 to 1, and then r. Okay, I will write domain D here, and domain D is the projection of this solid E onto the xy plane. Now let's see what this domain D is. Now if you look from the top, then you will see a circle with radius 1. You will see the boundary of the cylinder, and it is a circle with radius 1. So now this triple integral, now we can figure out the limits of the first 2 integrals. The middle integral corresponds to the r variable, and r goes from 0 to 1. The outer integral corresponds to the theta variable. Theta goes from 0 to 2 pi, because we have a full circle. Okay, so let's do this integral. Yes, integral from 0 to 2 pi. Middle integral goes from 0 to 1. The inner integral goes from -1 to 1. We have c squared r cube dc dr d theta. As you can see, we have a very simple integral. But if you do this integral in Cartesian coordinate system, you will get a very complex integral. Okay, so my first variable of integration is c. With respect to the c variable, r cube is a constant, and we can pull out a constant from the integral sign. Okay, cube -1 to 1, c squared dc, then dr d theta. Okay, integrate c squared. Integral of c squared is c cubed over 3. Lower limit is -1, upper limit is 1. Apply the upper limit first. You have 1 cubed over 3 minus -1 cubed over 3 dr d theta. -1 to the power 3 is -1. -1 times this negative becomes +1. We have the same denominator. Therefore, this constant becomes 2/3. which is a constant. So this is 2/3, and we can pull out that constant 2/3 from the integral signs. So you have 2/3 times the integral from 0 to 2 pi, integral from 0 to 1, r cubed dr d theta. Integral of r cubed is r to the power 4 over 4 apply the upper limit first. You will get 1/4 minus 0 over 4 1/4 is a constant, and let's pull out that constant from the last integral. Integrate 1 with respect to the theta variable, we get theta. Lower limit is 0, upper limit is 2 pi. We have 2 over 12 times this. If you simplify this one, you will get 2 over 12 times 2 pi, which equals to pi over 3. Now this is the way we use cylindrical coordinates to solve a triple integral. Now as you can see in this particular problem, our domain is a cylinder. So it is very intuitive to use a cylindrical coordinate system to solve a triple integral like this.